So now let's look at how we would actually solve a circuit that is a balanced three-phase system. So the first thing that we need to understand is that if the system is balanced, the phase voltages differ by a factor of 120 degrees. And because voltages and currents are all related by Kirchhoff's laws, we could demonstrate by proof, we won't, but we could demonstrate that really, if we find all of the currents and voltages in one of the legs of the system or one of the phases, that we've essentially found it in all of the phases. We only have to add and subtract 120 degrees in phase from the result of a single phase. So what the next figure shows is how we actually solve the circuit is we actually pull out what we call a single phase or a single loop equivalent. So we're going to just pull out one of the phases of the three-phase system. And usually it's most convenient to do this on the leg that has the phase angle of 0, which is referred to as the reference phase when speaking of the ideal part of the source. So most of the time problems are set up where the A phase is the reference phase, meaning it'll have a phase angle of 0. And so this just illustrates our single phase equivalent circuit. So notice that we only have the A prime or the AA part of the transmission line, we have the A part of the load, we have the A part of the generator. And each impedance, the generator impedance, the line impedance, and load impedance, they're all modeled here in this single phase equivalent circuit, and the neutral wire is also modeled. Now one comment, you'll notice that since we only pulled out one single phase, the current for this circuit as shown in the neutral wire is not 0 because it's a single loop. So for our equivalent circuit, the neutral wire will have a current equal to the line current, I little a big A. Now when we reassemble the three-phase circuit and include the B and the C phases, that neutral wire current will actually be the sum of all three. And remember, the phasor sum of a balanced three-phase circuit will go to 0 because they'll all be of the same magnitude and 120 degrees out of phase with each other. So this is one of the practical issues that can plague three-phase systems, is if your load or your generator or your line has a fault, and it doesn't have to be a major fault, it can be a minor fault, just a minor flaw that makes some little difference between the phase, between the impedances in A, B, and C where you're slightly off balance, then what happens is you get current in the neutral wire, and that can feed back into your generator and create problems, and it also wastes energy. So good three-phase systems have continuous monitoring systems that determine that all of the systems are indeed balanced so that you don't have issues with currents and voltages showing up across places where you don't want them. If you have no neutral wire, which is sometimes the case, then basically you'll end up with a voltage between your generator and your load. The current due to that voltage will have nowhere to go except back down the transmission lines in the reverse direction, so that's a problem as well. So the single phase equivalent circuit, we do have to calculate this loop current if we want to know excuse me, if we want to know the current in the line and in the load. But just remember that when the circuit's reassembled as a three-phase system, the neutral wire current remains 0. So here are a couple of definitions that I alluded to earlier. In a three-phase system, we're often interested in what are the voltages at the load. And so there are a couple of different kinds of voltages that are defined. First of all, here is the point, here's what we call the neutral point. The phase voltages in a Y-connected system, so the load here is in a Y-connected system. The phase voltages occur between the phase transmission line, so here's point A, and the neutral. So the phase voltages are the voltages here shown in blue. VAN is from the A wire to the neutral. VBN is from the B wire to the neutral. VCN is from the C wire to the neutral. So those are the line to neutral voltages, also referred to as the phase voltages. The line to line voltages would be the voltage that you would measure from one line to another, shown in black. So for example, from point A to point B, across two of the lines, we would have VAB, the line voltage. From C to A, we would have VCA. From B to C, we would have VBC. So the voltages shown in black are line voltages, or line-to-line voltages. And they're not the same, but we could figure out what they are if we just wrote a KVL equation around a loop here. So we could write a loop here, we could write a loop here, and we could write a loop around the entire outside. And we could also show that if we use phasor diagrams, we could show that those line voltages are 30 degrees out of phase with the phase voltages. So looking at our single phase equivalent circuit, basically it's going to look like this. This is an example problem. So if we were to write, obviously the way to solve this is we have a known voltage, we have a bunch of known impedances. So the first thing to solve for is the current I little a big A. And then once we have that, we can find any drop in the system because we know the current. So we can find the drop at the generator end from little a to neutral. It will not be 120 angle 0 because this is an ideal voltage and hasn't included the voltage drop due in the source. So the actual output voltage would be this voltage between A and N. We could find the voltage drop down the line, and we could find the voltage drop at the load end. So that's the approach. When you have a Y to Y configured circuit, the first thing you want to do is you want to draw your single phase equivalent. After you draw your single phase equivalent, the next thing you want to do is you want to find your line current, or the current in that single phase. Once you found the line current, you can find any other voltage in the system. Once you found the voltages in phase A, you can find, and currents, you can find voltages and currents in phase B by doing what? Subtracting 120 degree phase. So it's going to have the same magnitude, but a different phase. Once you find the voltages in phase B, you can also find the voltages in phase C by taking the voltages in phase A and adding 120 degree phase. So it becomes very iterative, and you really only have to solve this one very simple single loop circuit. So the main key in three phase is not to overcomplicate the problem, which is easy to do. All right, the next video I want to show an example, and what we're going to do is walk through the example, the part where we're looking for the phase voltages and phase currents. And then I want to go back and do a little more detail about how we get from phase currents to line currents. There are a few really simple equations based on some of the figures we've seen earlier. But first of all, we'll step through how to find the phase voltages and the line currents. So that's actually included in an example on the next video.